At its core, what enables each wave and each phase of AI, three fundamental matters are involved. The first is how do you solve the data problem? And the reason why that's important is because AI is a data-driven computer science approach. It needs data to learn from. It needs digital experience to learn from, to learn knowledge and to gain digital experience. How do you solve the data problem? The second is how do you solve the training problem without human in the loop? The reason why human in the loop is fundamentally challenging is because we only have so much time, and we would like an AI to be able to learn at superhuman rates, at super real-time rates, and to be able to learn at a scale that no humans can keep up with. And so the second question is, how do you train the model? And the third is, how do you scale? How do you find an algorithm whereby the more resource you provide, whatever the resource is, the smarter the AI becomes? The scaling law. Well, this last year, this is where almost the entire world got it wrong. The computation requirement, the scaling law of AI is more resilient and, in fact, hyper-accelerated. The amount of computation we need at this point as a result of agentic AI, as a result of reasoning, is easily 100 times more than we thought we needed this time last year. You can't just accelerate software, just as we needed an AI framework in order to create AIs, and we accelerate the AI frameworks. You need frameworks for physics and biology and multi-physics and all kinds of different quantum physics. You need all kinds of libraries and frameworks. We call them Cuda-X Libraries, acceleration frameworks for each one of these fields of science. This is just a sampling of the libraries that make possible accelerated computing. It's not just CUDA. We're so proud of CUDA. But if not for CUDA and the fact that we have such a large installed base, none of these libraries would be useful for any of the developers who use them. For all the developers that use them, you use it because, one, it's going to give you incredible speed up. It's going to give you incredible scale up. And two, because the install base of CUDA is now everywhere. It's in every cloud. It's in every data center. It's available from every computer company in the world. It's literally everywhere. And therefore, by using one of these libraries, your software, your amazing software, can reach everyone. And so we've now reached the tipping point of accelerated computing. CUDA has made it possible. And so today, I'm super excited to announce that GM has selected Nvidia to partner with them to build their future self-driving car fleet. The time for autonomous vehicles has arrived, and we're looking forward to building with GM AI in all three areas. AI for manufacturing, so they can revolutionize the way they manufacture. AI for enterprise, so they can revolutionize the way they work, design cars and simulate cars, and then also AI for in the car. So AI infrastructure for GM, partnering with GM, and building with GM their AI. So I'm super excited about that. All right, let's talk about data centers. Well, our goal is to do this. Our goal is to do scale up, and this is what it now looks like. We essentially wanted to build this chip. It's just that no reticle limits can do this. No process technology can do this. It's 130 trillion transistors. 20 trillion of it is used for computing. So it's not like you can't reasonably build this anytime soon. And so the way to solve this problem is to disaggregate it, as I've described, into the Grace Blackwell NVLink 72 rack. But as a result, we have done the ultimate scale-up. This is the most extreme scale-up the world has ever done. The amount of computation that's possible here The memory bandwidth, 570 terabytes per second. Everything in this machine is now in T's. Everything's a trillion. And you have an exaflops, which is 1,000,000 trillion floating point operations per second.
Traditional LLMs capture foundational knowledge, while reasoning models help solve complex problems with thinking tokens. Here, a prompt asks to seat people around a wedding table while adhering to constraints like traditions, photogenic angles, and feuding family members. Traditional LLM answers quickly with under 500 tokens. It makes mistakes in seating the guests, while the reasoning model thinks with over 8,000 tokens to come up with the correct answer. It takes a pastor to keep the peace.
And so today we're announcing the Nvidia Dynamo. Nvidia Dynamo does all that. It is essentially the operating system of an AI factory. Whereas in the past, in the way that we ran data centers, our operating system would be something like VMware. And we would orchestrate, and we still do, we're a big user, we orchestrate a whole bunch of different enterprise applications running on top of our enterprise IT. But in the future, the application is not enterprise IT, it's agents. And the operating system is not something like VMware, it's something like Dynamo. And this operating system is running on top of not a data center, but on top of an AI factory. We're now in full production of Blackwell. Computer companies all over the world are ramping these incredible machines at scale. And I'm just so pleased and so grateful that all of you worked hard on transitioning into this new architecture. And now, in the second half of this year, we'll easily transition into the upgrade. So we have the Blackwell Ultra NVLink 72. It's 1.5 times more flops. It's got a new instruction for attention. It's 1.5 times more memory. All that memory is useful for things like KV cache. It's 2 times more bandwidth, okay, for networking bandwidth. And so now that we have the same architecture, we'll just kind of gracefully glide into that, and that's called Blackwell Ultra. The next click, 1 year out, is named after an astronomer, and her grandkids are here. Her name is Vera Rubin. She discovered dark matter. Okay, yep. Vera Rubin is incredible because the CPU is new. It's twice the performance of Grace, and more memory, more bandwidth, and yet just a little tiny 50-watt CPU. It's really quite incredible. Okay, and Rubin, brand new GPU, CX9, brand new networking smart NIC, NVLink 6, brand new NVLink, brand new memories, HBM4. Basically, everything is brand new except for the chassis. And this way, we could take a whole lot of risk in one direction and not risk a whole bunch of other things related to the infrastructure. And so Vera Rubin, NVLink 144, is the second half of next year. And then this now sets the stage for the second half of the year, the following year, we call Rubin Ultra. Okay, so Vera Rubin Ultra. I know. This one is where you go, all right, so this is Vera Rubin Ultra, second half of 27. It's NVLink 576, extreme scale up. Each rack is 600 kilowatts, 2.5 million parts, okay? And obviously a whole lot of GPUs. And everything is X factor more. So 14 times more flops, 15 exaflops. Instead of 1 exaflop, as I mentioned earlier, is now 15 exaflops, scaled up exaflops, okay? And it's 4.6 petabytes, so 4,600 terabytes per second scale up bandwidth. I don't mean aggregate, I mean scale up bandwidth. And of course, a brand new NVLink switch and CX9, okay? And so notice 16 sites, 4 GPUs in one package, extremely large NVLink. Now just put that in perspective. This is what it looks like, okay? Now this is going to be fun. So you are just literally ramping up Grace Blackwell at the moment, and I don't mean to make it look like a laptop, but here we go. Okay, so this is what Grace Blackwell looks like, and this is what Rubin looks like. ISO dimension. First of all, we're announcing NVIDIA's first co-packaged option, silicon photonics system. It is the world's first 1.6 terabit per second CPO. It is based on a technology called micro-ring resonator modulator, and it is completely built with this incredible process technology at TSMC that we've been working with for some time. This is what a PC should look like. 20 petaflops. Unbelievable, 72 CPU cores, chip-to-chip interface, HBM memory, and just in case, some PCI Express slots for your GeForce. Okay, so this is called DGX Station. DGX Spark and DGX Station are going to be available by all of the OEMs. HP, Dell, Lenovo, Asus. It's going to be manufactured for data scientists and researchers all over the world. This is the computer of the age of AI. This is what computers should look like. And this is what computers will run in the future. And we have a whole lineup for enterprise now, from little tiny one to workstation ones, the server ones, to supercomputer ones, and these will be available by all of our partners. And they turn into these switches. Our InfiniBand switch, the silicon is working fantastically. Second half of this year, we will ship the silicon photonics switch in the second half of this year. In the second half of next year, we'll ship the Spectrum X. All right, so this is our roadmap once a year, an architecture every 2 years, a new product line every single year, X factors up, and we try to take silicon risk or networking risk or system chassis risk in pieces so that we can move the industry forward as we pursue these incredible technology. Vera, Rubin, and I really appreciate the grandkids for being here. This is our opportunity to recognize her and to honor her for the incredible work that she did. Our next generation will be named after Feynman. And so today we're announcing something really, really special. It is a partnership of 3 companies, Deepmind, Disney Research, and Nvidia, and we call it Newton. Hey, Blue. How are you doing? How do you like your new physics engine? You like it, huh? Yeah, I bet. I know. Tactile feedback, rigid body, soft body simulation, super real time. Can you imagine just now what you were looking at is complete real time simulation? This is how we're going to train robots in the future. Just so you know, Blue has 2 computers, 2 NVIDIA computers inside. Look how smart you are. Yes, you're smart. Okay. All right. We have another amazing news. I told you the progress of our robotics has been making enormous progress. And today we're announcing that Groot N1 is open sourced. Well, have a great GTC. Thank you. Hey, Blue. Let's go home. Good job. Good little man.